we were trying to obtain numerical methods which are exact for polynomials of degree greater than n when we make use of n points which are nodes in an interval, and we said that this is possible when we choose the nodes as the zeros of Legendre polynomials of degree n. We use this idea proposed by Gauss and obtain Gauss integration formula when n is equal to 2. So, let us now obtain Gauss integration method when n is equal to 3 and see what we get. So, when n is equal to 3, we require an integration formula of the form integral minus 1 to 1 f of x dx is equal to c1 into f at x1 plus c2 f of x2 plus c3 f of x3, where c1, c2, c3 are unknown constants to be determined, and x1, x2, x3 are again unknown nodes to be determined, such that x1, x2, x3 lie in the interval minus 1 to 1 in such a way that this integration method, which I call as star, is exact for polynomials of degree less than or equal to 2n minus 1. So, in this case it is 2 into 3 minus 1, that is 5. So, you have used only 3 nodes in the interval minus 1 to 1. So, 3 points and information of the function values at these 3 nodes here are required, but you are able to get an integration method which is exact for polynomials of degree greater than 3. In fact, the method that we will derive is going to be exact for polynomials of degree less than or equal to 5. So, the procedure is that we want it to be exact for polynomials of degree less than or equal to 5. So, let us take it to be 1 x, x square, x cubed, x to the power of 4 and x to the power of 5. So, when you impose these conditions, namely integral minus 1 to 1 dx will give you c1 plus c2 plus c3, and that must be equal to x between minus 1 and 1. So, that will give you this is equal to 2. So, we can write down the other conditions, namely minus 1 to 1 x dx will be x square by 2 between minus 1 and 1, and that will be 0. So, that will give you c1 x1 plus c2 x2, because f of x is x, plus c3 into x3, and that is equal to 0. That gives you the second condition. And thirdly, minus 1 to 1 x square dx. So, that will be x cubed by 3 between minus 1 and 1. So, 2 by 3, that will give you c1 x1 square plus c2 x2 square plus c3 x3 square, and that must be equal to 3. And then integral minus 1 to 1 x cubed dx, and that will be equal to 0, and that will be c1 x1 cubed plus c2 x2 cubed plus c3 into x3 cubed. Integral minus 1 to 1 x power 4 dx will give you x power 5 by 5 between minus 1 and 1, namely 2 by 5 will be c1 x1 power 4 c2 x2 power 4 into c3 into x3 to the power of 4, and the final condition is given by integral minus 1 to 1 x power 5 by x power 5 dx, which is x power 6 by 6 between minus 1 and 1, and that will be 0, and that is equal to c1 x1 power 5 plus c2 x2 power 5 plus C3 into x3 to the power of 5. So, this gives you the sixth equation. So, using these 6 equations, we will be able to determine the unknown constants C1, C2, C3 and the unknown nodes x1, x2 and x3. So, we do the calculations which is similar to what we have done in the derivation of Gauss integration method for n is equal to 2. So, you get C1 into P3 of x1 plus C2 into P3 of x2 plus C3 into P3 of x3 will be 0 by orthogonality property. Then the next equation is C1 x1 into P3 x1 plus C2 x2 into P3 x2 plus C3 x3 into P3 x3 equal to 0. And you will end up with the third equation as C1 x1 square into P3 x1 plus C2 x2 square into P2 x2 plus C3 x3 square into P3 x3 equal to 0. So, now these equations will have to be satisfied, and we observe that for any choice of C1, C2, C3, if you take x1, x2, x3 to be the zeros of the polynomial P3 of x, which is a Legendre polynomial of degree 3, then this equation is identically satisfied. This is again identically satisfied, and the third equation will also be identically satisfied. So, we see that for any choice of C1, C2, C3, if x1, x2, x3 are taken as the zeros of P3 of x, then if I call this equation as double star is identically satisfied. So, let us see what are the zeros of P3 of x. We know that P3 of x is equal to half of 5x cube minus 3x. So, the zeros of P3 of x are given by x into 5x square minus 3 equal to 0. So, x is equal to 0 and x is equal to plus or minus root of 3 by 5. So, we have 3 zeros, namely the zeros are located at minus root of 3 by 5 at 0 and then plus root of 3 by 5, and they lie within the interval minus 1 to 1. So, I take this as x1, this as x2 and this as x3, and I am able to satisfy these equations identically for any choice of C1, C2, C3. So, now make use of this information and determine C1, C2, C3 by using any of these 3 equations. So, let us take the first equation that says C1 plus C2 plus C3 must be equal to 2. And the second tells me C1 into x1, that is minus root of 3 by 5 plus C2 into 0 plus C3 into root of 3 by 5 must be 0. So, this tells you that C minus C1 plus C2 is 0. That gives you another equation for C1, C2. The third one tells C1 into x1 square, so 3 by 5, C2 into x2 square plus C3 into x3 square, which is again 3 by 5. That must be equal to 2 by 3. That is the third equation, from which we obtain here the equation given by C1 plus C3 is equal to 5 by 3 into 2 by 3. So, it is 10 by 9. So, C1 plus C3 must be equal to 10 by 9, and this gives you that C1 is equal to this is C3. This tells you that C1 is equal to C3. and therefore C1 plus C3 is 10 by 9. So, C1 must be equal to C3 must be equal to 5 by 9. So, substitute there, therefore, C2 must be 2 minus C1 plus C3. So, this is going to be 8 by 9. So, we have been able to obtain the integration method when n is equal to 3, because we have determined C1, C2, C3 and x1, x2, x3. So, it tells us that when n is 3, the nodes are the zeros of P3 of x is equal to 0. Earlier we saw when n is 2, the nodes must be chosen such that they are the zeros of P2 of x is equal to 0. So, it is clear that if n is some k, then the nodes must be chosen in such a way that they must be the zeros of Pk of x is equal to 0, and the corresponding constants C1, C2, etc. Ck can be determined, and the method will be exact for polynomials of degree greater than k. In fact, they will be exact for polynomials of degree less than or equal to 2k minus 1. So, let us write down the details when n is 3. So, this tells us that integral minus 1 to 1 f of x dx is equal to C1, which is 5 by 9 into f of x1. What is x1? x1 is minus root of 3 by 5. C2 is 8 by 9. What is x2? 0. And C3 is again 5 by 9, f of root of 3 by 5. So, the method is 1 by 9 times 5 into f at minus root of 3 by 5 plus 8 into f at 0 plus 5 into f at root of 3 by 5. This is our 3-point Gaussian quadrature method. So, we have derived the 3-point Gaussian quadrature method. So, we again observe that the nodes lie in the interval minus 1 to 1. So, we have obtained an open type formula because the endpoints are not included. And another observation is that the nodes along with minus 1, 1 in this interval are such that these points are not equally spaced. However, these 3 nodes are such that 2 of these nodes x1, x3 lie symmetrically on either side of this node, namely which is located at the origin. So, we have sacrificed the requirement that the nodes must be equally spaced, but this has yielded a method which is such that the integration method is exact for polynomials of degree greater than n when we make use of the information of the function values at n nodes which lie within this interval. That is the beauty of Gaussian quadrature techniques. So, one can go on and derive Gaussian quadrature methods for any value of n, and you know where the nodes should lie. You only have to solve for the constants C1, C2, C3, etc., Cn depending upon what you choose your n as. So, let us illustrate this by means of an example. So, find the value of the integral, say I, which is integral 2 to 3 cos 2x by 1 plus sin x dx. So, obtain this using Gauss 3-point integration method. We have already done this using 2-point method. Let us work this out using 3-point method. So, since the interval of integration is from 2 to 3, we must change this interval to minus 1 to 1. So, we use the transformation that x is equal to t plus 5 divided by 2. So, that 2 dx will be equal to dt. So, this will be equal to integral half of minus 1 to 1 cos of 2 into 2x is t plus 5. So, I can substitute cos t plus 5 divided by 1 plus sine of t plus 5 by 2 into dt. So, I have integration between minus 1 and 1 of some function, right, some integrand. So, I directly apply Gauss 3-point formula. So, I have half into, if I apply Gauss method, it is going to be 1 divided by 9 into 5 times the function value at minus root of 3 by 5. The function is this. So, cos of minus root of 3 by 5 plus 5 divided by 1 plus sine of minus root of 3 by 5 plus 5 by 2. And then I have plus 8 times f at 0. So, cos of 0 plus 5 divided by 1 plus sine 0 plus 5 by 2. And then the next term 5 cos of root of 3 by 5 plus 5 divided by 1 plus sine of root of 3 by 5 plus 5 by 2. So, this gives you the value of the integral. You can get these values and show that this turns out to be 0.20271391. So, that is the value of the integral when you use a 3-point Gaussian method. And suppose you are asked to say, you are asked to evaluate this integral correct to say 4 decimal accuracy, then the solution will be I is equal to 0.2027, because you see what the next digit is, it is 1 less than 5, and therefore, the solution correct to 4 decimal places is 0.2027. So, please use this technique of 3-point Gaussian integration method and solve the following. Show that integral 1 to 5 root of 1 plus x square dx is equal to 41.71. Evaluate integral 0 to 1 dx by cube root of 1 plus x square. Evaluate using Gaussian 3-point formula. And then you also take the following as a homework and try it out. Derive 5-point Gaussian quadrature formula. So, that completes our discussion on Gaussian quadrature methods. So, in all the methods that we derived so far, we took the step size h to be a constant. But there are situations where in an interval there is a subinterval where the function variations are very large, whereas some other portion of that interval the function variations are very slow. In such cases, it is important that we take the step size in that interval where the function varies rapidly to be very small, to account for the large variations in the function in that interval, and in another part of the interval the step size need not be as small as we take here, because the variation of the function in that interval is very, very slow. So, it is important that an integration method or a quadrature rule that should be derived so that it automatically changes its step size and accordingly perform the integration using the rule that we want to use, and then gives us the value of the integral correct to the desired degree of accuracy. So, we would like to know such an integration method. When we do this, the resulting method that we are going to give now or explain is capable of taking appropriate step size in some intervals where the integration has to be performed, so that it accounts for the variations in the function, whether it is a large variation or a small variation. Such integration methods are called adaptive quadrature methods. Adaptive quadrature rules or methods. So, let us now derive the adaptive quadrature technique, which is based on Simpsons rule. So, Simpsons rule tells us that integral a to b f of x dx is h by 3 f of a plus 4 f of a plus b by 2 plus f of b, and the error involved is of order of h power 5, where h is b minus a by 2. So, when I use that, then the error term can be written as h power 4 into b minus a by 180 into fourth derivative at psi, where psi lies between a and b. So, let us now derive Simpsons rule based adaptive quadrature method. So, in step 1, I apply Simpsons rule with step size h and write down the rule. In step 2, I divide the interval a b into 4 equal subintervals of width h1, which is b minus a by 4. So, it is half the step size of the earlier step. So, the 4 points are going to be a plus b by 2 and the midpoint of that interval, then a plus b by 2b and the midpoint of that subinterval. So, we apply Simpsons rule or composite Simpsons rule in this interval a to b, which is divided into 4 equal subintervals. So, you get h by 6. I would have written this as h1 by 3, but h1 is h by 2. So, it is h by 6 into sum of the end ordinates f of a plus f of b plus 4 times the intermediate ordinates, which are odd suffixed, and 2 times the value of the function at the even suffixed ordinate. And now, this can be expressed in the form h by 6 into f of a plus 4 f of 3a plus b by 4 plus f of a plus b by 2, and then plus f of a plus b by 2 plus 4 f of a plus 3b by 2, a plus 3b by 4 plus f at b. So, when I have divided this into 4 equal parts, what is the error that is incurred? H is now h by 2, and so h power 4 will give you h power 4 by 16 into 180 into b minus a into fourth derivative evaluated at that psi, where psi lies between a and b. So, now I write this into 2 parts, and I see that the first term corresponds to Simpsons rule in the interval a to a plus b by 2, and the second term gives me Simpsons rule in a plus b by 2 to b, and the error incurred is minus h power 4 into b minus a by 16 into 180 into the fourth derivative at psi for a less than psi less than b. So, I write down this as I is therefore I of, what have I done? I have applied Simpsons rule in a to a plus b by 2. So, I shall call this as a to a plus b by 2, and the next term corresponds to a plus b by 2 comma b. So, I have applied Simpsons rule in that subinterval. So, earlier I was written as I of AB, where you had applied Simpsons rule in that interval AB by dividing it into 2 equal subintervals. Now, the same I is expressed as I of a plus b by 2 plus I of a plus b by 2 comma b. So, now we observe that, and the error incurred is minus h power 4 by 16 into 180 into b minus a into the fourth derivative at psi. So, that I minus I will give me 0, and that is equal to I of a b minus I of a comma a plus b by 2 minus I of a plus b by 2 comma b, and that will be equal to, what is the error that is incurred? The error that is incurred is minus h power 4 into b minus a by 180 into the fourth derivative at psi. We can even take here psi 1 and this as psi 2 and replace the psi in such a way that the maximum of the fourth derivative of f at psi 1 and the fourth derivative of f at psi 2 is given by the fourth derivative of f at psi. So, I am replacing that here as psi. And then what does the error from the next term give? Because I am subtracting, that is plus h power 4 into b minus a by 16 into 180 into the fourth derivative at psi for psi lying between a and t. So, if you want, you can replace this by fourth derivative at psi 1 and this as fourth derivative at psi 2 and say that the fourth derivative of psi is maximum of the fourth derivative of f at psi 1 and fourth derivative of f at psi 2 for psi lying in a to b. So, we have replaced it by the fourth derivative of f at psi. So, what does this give? This gives you minus 16 plus 1. So, minus 15 times h power 4 b minus a by 180 into the fourth derivative at psi, or in other words you get 1 by 15 of I of a b minus I of a comma a plus b by 2 I of a plus b by 2 b is minus h power 4 into b minus a by 180 into fourth derivative at psi. What was this? What was this? Do you recall? This is essentially the error that you get here in evaluation of this integral I by applying Simpson's rule, and that says that error is 1/15th of the difference between applying Simpson's rule in an interval a b and then applying Simpson's rule in the interval after dividing a b into 4 equal parts. That is what this step says. And therefore, we have the absolute value of the difference between a b and a plus b by 2, a plus b by 2 comma b, right. This difference in absolute value is going to be what? Or I can replace this I of a b by the integral itself, integral a to b f of x dx. So, the difference in the exact integral minus the value that you get by applying Simpson's rule is such that it is going to be 1 by 15 of IAB minus I a plus b by 2 minus I a plus b by 2 comma b. So, this is what you get. So, therefore, you now specify the test. If this quantity 1 by 15 into absolute value of I of AB minus I A plus B by 2 minus I A plus B by 2B, if this quantity on the right hand side in absolute value turns out to be, say, less than epsilon, namely the accuracy that you prescribe, then what does it mean? Then it means you can take your value of integral I, integral a to be f of x dx, to be equal to I of a plus b by 2 plus I of a plus b by 2 comma b, namely by applying the Simpsons rule to each of the half intervals into which you have divided the interval a b into, and your solution or your result will be correct to the desired degree of accuracy, because you have made sure that the error that is incurred is less than epsilon. So, all this should be done in step 2. So, I repeat step 2 again. Step 2 is equivalent to doing the following: divide the interval a b in such a way that it is split into 4 equal subintervals, and composite Simpsons rule is applied in that interval. The result tells you that it is equivalent to applying Simpsons rule in each of these half intervals a to a plus b by 2 and a plus b by 2 to b. And when you write down the expression for the error and compute what is the difference between IAB and this, then 1 by 15 of this gives you an error which is exactly the expression that you have over here. And therefore, if you can make that error small according to what you require, namely correct to the desired degree of accuracy, namely if 1 by 15 of this turns out to be less than epsilon at the end of your computations, then you are through. Namely, you have obtained the value of the integral correct to the desired degree of accuracy, namely this. So, the question arises, what if this does not happen? Suppose I call this as star. So, if star does not hold. So, you observe that in absolute value 1 by 15 of this is not less than epsilon, then what do? You perform step 3. What is your step 3? Step 3 is take the interval a to a plus b by 2 and the interval a plus b by 2 to b. Call this as, say, interval a1 b1 and b1 b. You just name this, and now you apply Simpsons rule in this interval a1 b1. All right, and also apply Simpsons rule in b1 to b. So, now you have to do two things at this step. Your interval now is a1 b1 to start with. So, there are two parts to it. One is you should apply Simpsons rule to interval a1 b1, and the second part is apply Simpsons rule to b1 to b. Let us first do the first part. So, apply Simpsons rule to a1 b1. Then what are you doing? You are essentially doing something like step 1 in an interval a b, all right. And then if you do that, then you will have I of a1 b1. And then what should you do? You should perform step 2 in the interval a1 b1, right. What does that mean? So, perform step 2 to the interval a1 b1. What will you get? You will get I of a1 comma a1 plus b1 by 2 plus I of a1 plus b1 by 2 comma b1. That will be your integral I when you perform. So, essentially the first part of step 3 is repetition of step 1 and step 2, but now the interval of integration is a1 b1. Now check whether the condition, accuracy condition star is satisfied, where in a1 b1, but now take your epsilon as epsilon by 2. So, take your epsilon say as epsilon 1, which is epsilon by 2, and check if 1 by 15 of I of a1 b1 minus I of a1 plus a1 a1 b1 minus I of a1 comma a1 plus b1 by 2 minus I of a1 plus b1 by 2 comma b1 in absolute value is less than what? Epsilon 1, that is epsilon by 2. Check whether this happens. Now you know if that happens, right, if the error is less than epsilon by 2, then you can take integral a1 to b1 f of x dx to be equal to this I of a1 plus b1 by 2 plus I of a1 plus b1 by 2 comma b1. All right. If that does not happen, then what should you do? You should take a1 plus b1 by 2 and call it as some a2 comma b2 and perform steps 1 and 2 for a2 b2 and do the test given by star. With what accuracy? Such that the error is less than some epsilon 2, where epsilon 2 is epsilon 1 by 2, namely epsilon by 4, and continue this process. This is for the first part a1 b1. Similarly, you should do everything for the second part b1b. If suppose the condition is not satisfied even in one of the intervals, right, you should continue to apply this procedure of repeating step 1 and step 2 to that particular interval again and again. So, continue this procedure. So, you may ask, will it converge? Do you think that the error will reduce? Yes, we observe that the error that you commit every time is 1 by 15 of the error that you have here. So, every time when you perform these steps, the error gets reduced by 1 by 15, and therefore, at some stage after finite number of steps, your error will be less than the prescribed epsilon with which you had started, and you have an adaptive quadrature technique that takes care of the step size appropriately, and that is what is adaptive quadrature method.